Hello, everyone. My name is Steve Studelsky. I'm the Liquid Platform Manager at Galvanic Applied Sciences in Massachusetts. Today, we have a technology comparison for the determination of oil and water. First, we'll give an instruction to hydrocarbons and oil removal processes. Then, we'll discuss the challenges faced for oil and water separation and monitoring. We'll conclude with sharing the available methods and where they perform best. There are three main categories of hydrocarbons, characterized as total petroleum hydrocarbons or total oil and grease. Saturated hydrocarbons include aliphatic hydrocarbons such as alkanes or paraffins, and alicyclic hydrocarbons such as cycloalkanes or naphthanes. Unsaturated hydrocarbons include olefins and alkenes. They're not usually found in crude oil but are produced in refinery cracking processes. Aromatic hydrocarbons are characterized by a benzene ring structure. Total oil can be broken down into dissolved oil and dispersed oil. Dissolved oil is in soluble form and normally consists of aromatic hydrocarbons and organic acids. Dispersed oil is in many droplets ranging from submicron to hundreds of micron in size. This oil contains both aromatic hydrocarbons and aliphatic hydrocarbons. As we all know, oil and water do not mix together. For example, for straight-chain saturated hydrocarbons, as the carbon number increases, the solubility decreases rapidly. There are several industrial processes where oil and water interact. Oil and gas production lead to the creation of produced water. As highlighted by the diagram on the right, the refining of oil leads to the creation of vast amounts of sour water. Industrial plants operating boilers or cooling towers can also have heat exchange fluid leak into their steam water circuit that must be treated. Oil must be removed from this water so the discharge meets environmental compliance. If the plant wants to recycle the water to be used in another process unit, the oil must be removed to avoid operational issues. Treating oil and water requires several steps due to the complex stream composition, which can include soluble and non-soluble oil, suspended solids, organics, dissolved solids, heavy metals, and various chemicals. Primary treatment removes a rough cut of oil and grease and total suspended solids. API use gravity separation and are only meant for high levels of hydrocarbons. API separators are designed according to the American Petroleum Institute standards. The API outlet should have a much lower concentration of oil than at the inlet. Another type of primary treatment is free water knockout. This is a three-phase separator and can segregate oil, gas, and free water. The vessel is also known as an oil and water separator. Coalescing systems are used for primary treatment. These are sometimes referred to by their brand names such as Schlumberger Wemco pacesetter separators. Secondary treatment utilizes various flotation units as well as coagulation. This includes dissolved air flotation and induced gas flotation. DAFs remove suspended solids and oils by dissolving air in the wastewater under pressure and then releasing the air at atmospheric pressure in a flotation tank. The released air forms bubbles which adhere to the suspended matter, causing the suspended matter to float to the surface of the water, where it may be then removed. IGF is another clarifying process that injects gas bubbles into the flotation tank. Tertiary treatment normally includes nutshell filtration systems to reduce oil and grease and total suspended solids down to low ppm levels. Commonly called walnut shell filters, these systems are used for ppm oils and solids. No chemicals are required for this process. Tertiary treatment also employs other filtration and ion exchange resin methods. This should leave the water almost oil-free so it can be discharged, used for steam generation, or recycled to another process unit. If there is an upset and oil remains, substantial cleaning is required, and if there is too much oil, the water must be thrown away, which becomes expensive. Each of these treatment processes benefit from monitoring their efficiency. This can be achieved using an instrument to measure the oil and water concentration. Operators should consider which method of analysis works best at each process. This is because the concentration of oil varies greatly from influent to effluent. Laboratory reference methods are important for providing meaning to discharge limits and performance standards in order to guarantee compliance. It's important to recognize that the different methods will produce different results. Each method requires different instruments, procedures, training, and investment. Infrared-based methods are well established, but they require expensive solvents and lack compositional detail. Gravimetric methods are simple and cheap, lack compositional detail, and include some loss of volatile components due to evaporation. Gas chromatography with flame ionization detectors require no solvents and have the potential for providing compositional detail, but required skilled operators. Portable field meters can be used for routine analysis and may be correlated to reference methods. Alternatively, online analyzers can be used for continuous analysis for process trending and detection of process upsets. Online monitoring of oil and water comes with sample and operational challenges. Multiple streams may have different types of hydrocarbons or be at different concentration range, which makes calibration difficult. The presence of gas bubbles, color, or suspended solids can affect performance. Inconsistent pressure, flow rate, and temperature can also have adverse effects. Sample systems used to create uniform dispersion may require maintenance. Inline installation makes sensor retrieval more difficult for scheduled maintenance. Sampling from bypass lines must ensure the fluid reflects real-time conditions. For these reasons, you should make sure you understand all available technologies. Light scattering analyzers perform ratio measurements of scattered to direct light. These are ideal for low concentrations of oil and water. Installation is available for both pipe and flange mounted. These systems include a reference filter to compensate for background turbidity. Near-infrared submersible sensors can also be used for oil and water. While these sensors are equipped with cleaning jets to handle higher concentrations of oil and water to avoid maintenance issues, they're best for lower ranges. Challenges associated with light scattering analyzers are primarily process upsets. Being an optical device, if the optics get followed, the results are no good. Process upsets would require frequent cleaning of the optical components. This method is also susceptible to interferences from background suspended solids. Scheduled maintenance for light scattering analyzers is annual O-ring replacement and replacing the source lamp and filters every 1 to 2 years. Ultraviolet photometry can also be used for low ranges of oil and water. Just like the NIR, even though the technology can measure higher ranges, to avoid maintenance issues, it's best to stick to lower concentrations. Installation is a 1/4-inch slipstream to either the sensor or a valve-mounted assembly. This allows the analyzer to perform multi-stream as well as automated cleaning. These systems also include a reference filter to compensate for background turbidity. Challenges associated with light scattering analyzers are primarily lamp drifting. Mercury source lamps are sensitive to temperature changes, which can occur due to enclosure purging, vortex cooling, or ambient temperature shifts. It's important that these systems employ a second fiber optic bundle for compensation. Just like light scattering technology, if the optic gets followed, the results are no good. This method is susceptible to interferences from other UV254 absorbing compounds. Scheduled maintenance for UV analyzers is weekly auto zero, annual O-ring replacement, and replacing the source lamp and filters every 1 to 2 years. Ultraviolet fluorescence is another optical method for oil and water that performs a sensitive measurement for very low to medium ranges of oil and water. This is probably the most widely used technology for oil and water detection. UV fluorescent uses a slipstream for installation, while laser-induced fluorescent can be used for probe-type installations. UV fluorescence depends on a constant oil droplet size. Homogenization helps only if the ratio of aromatics to total oil remains constant. Some chemical residuals can also be incorrectly detected as oil. This method is also highly sensitive to flow changes, especially when using UV lamps. Low flow samples become uneven in the detection cell, causing erratic readings. LAF systems can operate at wider ranges, but still read positive value if flow stops. Scheduled maintenance includes weekly manual calibration, where the sample stream is purged with DI and then a validation solution is injected. Every 6 months, you should check or replace the desiccant canister depending on the ambient humidity, as well as manually clean the flow cell. Recalibration is recommended every 6 to 12 months. Every 12 to 24 months, replace the ultrasonic probe in syringe port. Acoustic backscatter is one of the few non-optical methods available. It's also one of the only accurate measures for measuring high ranges of oil and water. The sensor can be flange or pipe mounted, as well as installed in an open channel. This technology is factory calibrated and does not require any maintenance. It handles coatings on the sensor, and cleaning is as simple as wiping it with a cloth. The advantage of acoustic systems is there's no optics to foul. The downside is that this method sees all particulates in the sample, including suspended solids and air bubbles. That's why it's important to mount the sensor away from flow disturbances. The sensor needs a minimum of a 3-inch pipe diameter for installation, or else a pipe adapter is required. The accuracy of acoustic devices is plus or minus 4% of full scale, compared to 2% for optical. In summary, you can see that each method has its own pros and cons. There are also specific measurement ranges where the technology does best. That's why when you're selecting an analyzer to measure oil and water, you should consider several factors specific to the project. This will ensure minimal maintenance headaches and smooth operations. We hope you've learned something new about measuring oil and water today. If you have any questions about how to optimize your process, please contact the Galvanic sales team, myself, or your local representative. Thank you and have a good day.